This video we briefly look at what is AC simulation, and I'm sort of going back to Neher's circuit which he had sent us, and I have sent a video about this earlier, in which you're using the op-amp as an amplifier, um, basically a gain of 100, and if I fed it 20 millivolts, then this is the output I get. It has a bias. Okay, that's a better way to look at it. I look at it after the AC, so I can look at input and I can look at output, and I can see there is a fairly large amplification that I get. And the amplification at this frequency, which is 10,000 kilohertz, 10,000 hertz, or 10 kilohertz, is almost the factor that we expect. 20 millivolt input, 2 volt output, almost a gain of 100. And okay, actually I'm just going to put 10 hertz. If I put 10 hertz and I run this simulation, I need to of course change my time. 10 hertz. Okay, 1 second. The amplification is significantly smaller. It's just a factor of 6, and earlier we had a factor of 100. So this amplification depends on frequency, and we know why it depends on frequency, because the capacitor is becoming more and more of an open, large resistance, large impedance here. It's getting closer to that, so we are getting a smaller and smaller gain. Now this you can check quite nicely by using the AC simulation. The first thing you have to do is you have to set a small signal AC analysis AC amplitude of 1, and then you have to change the simulation. You don't run a transient, you run an AC. So number of points per octave, okay, 20. Start frequency, what we just did, 10 hertz. Stop frequency, okay, let's say 100 kilohertz, 10 times more than where we simulated. Now I run this, I get some entirely different plots. So what I'm looking at is, what I'm interested in is in the output, so I'm just going to plot the output. Okay, so there are two plots, and this part is always confusing, but if you click on this, you get a cursor, and if you move the cursor around, it tells you what is the value, right? So it's actually giving you both the magnitude and the phase in this case. Very nice. Okay, so what you see here, and I've put it around, it should be 28, so it's this plot. This plot is basically on the left side, right? And so here you can see how much the amplitude is changing as a function of frequency. If I fed 1 volt, I would get a gain that was 16 dB here, and I would get that gain of 40 dB. Now let's see, what's 40 dB? 40 dB is 20 plus 20, which is 10 into 10, which is 100. So I'm getting the gain of 100, which is what I expect, only after a certain frequency, which is around 1 kilohertz. So around here I'm starting to get a gain of 100. So at 100 hertz I would have got a gain of around 34.5, around 35 dB. So 35 dB is almost 5 dB lower than 40 dB, so almost a gain of only half at 100 kilohertz, 100 hertz. So if I was getting an amplitude of almost 2 volt at 1 kilohertz or 10 kilohertz, I'm only going to be getting an amplitude of 1 volt at 100 hertz. This is what it is trying to convey. It's trying to convey what is the amplitude going to be of the output at the same frequency as the input. It is not conveying that your frequency is changing. It is only conveying that if I applied an amplitude of 1 at the input, then in an AC sense, which is a very small signal sense, it's not saying apply 1 volt to it. It's just giving you a scaling factor. Then you would get half the signal here, half the signal amplitude at the output there, here versus there. Okay, yeah, alright, so let's see. So let's go back to the transient, And what I'm going to do is I'm going to increase the frequency to what it said was at 100 hertz, right? So if I increase the signal to 100 hertz, I should get around 1 volt output. That's what it's telling us. So let's see. So we'll take the AC output. So the output amplitude is around 1 volt. This is what an AC plot gives you. It tells you what is the amplitude at different frequencies.